Hello, my name is Elliot Cassidy, and in this video I'd like to walk through the solution to question 3, Drats, from the 2006 British Informatics Olympiad. If you haven't already, please pause now to review the problem statement shown on screen. Per the problem statement, each Drat can award 1 to 20 points, with the initial Drat contributing double its nominal value. This structure naturally induces a tree representation. From a root node with score 0, each node branches to 20 children, representing possible subsequent throws. This branching continues recursively, with the tree depth corresponding precisely to the number of Drats thrown, d. If you are unfamiliar with graph theory, I recommend you read the section on graph theory in the Competitive Programmer's Handbook, which I have linked below in the description. To compute the number of distinct sequences yielding score S with d Drats, the intuitive approach is depth-first search. This recursive algorithm exhaustively explores each path before backtracking when 1. The current depth equals d and the accumulated score equals S, meaning we have found a valid solution. We increment the number of valid solutions by 1. 2. When the total exceeds the goal score S, further scores cannot yield valid solutions. This means further exploration of this branch is futile. 3. When the depth reaches the number of Drats d without achieving the goal score S, the path is invalid. Since each node branches to 20 children, this yields a time complexity of O of 20 to the power of n, where n is the tree depth, placing it in exponential time. Consequently, the number of operations increases massively as the tree gains layers. Whilst correct, this solution exhibits inefficiencies. Distinct paths may reach identical states, meaning they have the same depth and the same score, which forces recomputation of identical values. This renders this approach impractical for competition test cases due to time constraints. To optimize this, we employ dynamic programming, a method whereby computed states are cached in an array, eliminating redundant calculations. Each depth score pair is resolved once only. There are two implementations of dynamic programming. One is memoisation, a top-down approach where recursive solutions are cached. The other is tabulation, a bottom-up approach that systematically constructs solutions iteratively from base cases. Memoisation builds solutions by caching computed values. It is conceptually identical to recursion, except all calculated values are stored in an array. When solving problems using dynamic programming, the array that stores the calculated values is k-dimensional, where k is the number of non-constant parameters to the recursive function. Here, with two non-constant parameters, we use a two-dimensional array. The first dimension of this array is the number of Drats thrown, and the second dimension is the accumulated score. However, tabulation typically outperforms memoisation. The latter incurs recursive overhead. Each function call allocates a stack frame, decelerating execution. Tabulation avoids this as it constructs solutions iteratively within a loop, requiring only one stack frame. I recognize dynamic programming can often be challenging when first encountered. For deeper understanding, I recommend the dynamic programming section in the Competitive Programmer's Handbook, linked in the description below. Now that you grasp the core concepts behind solving this problem, I encourage you to attempt implementing a solution to this problem yourself. It's an excellent way to solidify your understanding. Afterwards, you may find it helpful to compare your solution against my annotated solutions available in the GitHub repository linked in the description below. If you found my video valuable, I would appreciate it if you could leave a like, and if you'd be interested in more content like this in the future, please do consider subscribing. Thank you for watching.